Hey guys, Mr. Myas is here, and in this video it's 3-5 related rates for Essentials of Calculus. So here we go, related rates. One of our, I guess this is our second really context type problem that we're doing in Calculus AB. We're going to look at how rates change, and we're going to use our previous lesson, which was on implicit differentiation, to do related rates. So let's take a look here, and the first thing I'd like you to do is I've got a lot of stuff and a recipe, if you will. Some steps that you're going to want to take a look at, because that's what I'm going to use as I go through these problems. All right, so let's take a look. Let me shrink myself down in the corner. There we go. All right, so a related rate is just a story problem. All right, it's just a context problem where we're looking at the rates of change with respect to time. So respect to time is what we're doing. So when we're going to do what we're going to do here for all these, we're going to take derivatives with respect to time. So that means if we have an x or a y or an s or a v or a j or a z, whatever it is, we're always taking the derivative with respect to time. It's a little bit different than what we previously did, which would we would always be taking the derivative with respect to x. That's why when we took a derivative of an implicit function, we just took the derivative of the x, but when we took the derivative of y, we had a y prime or a dy dx. So now what you'll see is anytime I take a derivative of anything that's not a t, I'm going to do d whatever dt. So I'm taking a derivative with respect to time. All right, so I'm going to be using that type of notation, d dt. Okay, so I just want you to look at the procedure. We're always going to try to draw a picture if we can. We need to find the derivative. Listen, there's really going to be a few things going on. We're going to have two things happening in this problem. One, we're going to have things that aren't changing, which are constant. Those need to be plugged in right away and represented with a number value. Anything that is changing within our problem, that you have to leave alone as a variable, because that's what we're going to need to take derivatives of, okay? Then we're going to implicitly differentiate both sides with respect to t, and then we're going to substitute any numbers or solve. One thing that does often happen sometimes is we might end up having to use one equation to plug into the equation that we're actually going to be doing derivatives of. So we might have another equation that's not really part of the differentiation. It's just part of allowing us to solve for a variable in our problem here. Okay, maybe you'll see a couple that doesn't happen all the time. A lot of times we can just take a derivatives of all the stuff that's changing. All right, so let's take a look. One of the things you're going to need to know are all these geometry formulas. So start thinking about these, guys. Remember these geometry formulas. If you don't, start memorizing them. All right, let's take a look at some examples. So these don't have any context to them really. This is the area of a square, s squared. So I'm going to do the first three steps of the procedure are already done. So we've already looked at the drawn the figure. We've already write what is given, and we already did all our equations. So what we're going to do is just look at the calculus part, which is 4 and 5, and then I'll show you some actual examples that we're going to be, or actual problems that we'd be doing. So given that a is equal to s squared, what we're going to do is take dA dt, because a is a variable. It's changing, the area is changing. If I think of a square, right? If I'm moving the square up and down, the area is changing as well as the sides. 2s ds dt. Now that I've taken the derivative, I can plug in the stuff that I know. I know that ds is 3, I know that s is 4, and that's 2. And so I'm solving in this case for dA dt. How do I know that? Because it says find dA dt. I'm going to do what it tells me to do, right? So 2 times 4 times 3 is 24. Now I don't have any units quite yet because I don't have any context. So let's just wait until I get some context to actually put some units down. Now I'm looking for dy dt. I know that dx dt is equal to -6. I know that y equals 4. I know that xy is equal to 12. Which of these things am I going to take a derivative of? Well, I'm not going to take a derivative of y because it's going to give me dy dt equals 0, which doesn't help me at all, right? Really what I'm going to do is I'm going to take this, and I want to take that derivative. However, Okay, so let's just go. We have to do that first before we plug things in, okay? Because I don't know that y is a, I don't know anything is a constant yet. So kind of my rule of thumb is you should really be taking derivatives before you plug in anything into a related rate problem, especially when we're talking about these contexts. You'll see what I mean in just a second. So I'm going to take the derivative of this. Implicitly, I've got to use the product rule. So that states I'm going to take the derivative of the first, which is 1 times oops, 1 times, so the derivative of x is 1 times y. Sorry, the derivative of x is dx dt. I was almost thinking back when I was taking with respect to x, but we're taking with respect to t. So, you know, we got to do dx dt. Got to have respect for the t. Plus x times dy dt equals derivative of 12 is 0. Now that I've taken the derivative, I can plug in my values. So I know that dx dt is -6. I know that y is 4. I don't know what x is, but I'm going to find it right now. And I'm looking for dy dt. All right, so now how do I know what x is when y is 4? Well, I can just plug that in now, and I can get 4x equals 12. I'm going to put this in a different color so you know that I did it after I took my derivative. 4x equals 12. So x is 3. So I'm going to plug that guy now in here. Okay, notice I didn't do that until after I took a derivative. And then I'm going to go and solve for x now. Okay, so I'm going to get 3 dy dt is equal to positive 24. And dy dt, after dividing over my 3, is going to be 8. All right? Okay, so let's take a look at some of the problems here that are word problems. Word problems in calculus? Yeah, let's not call them word problems. Let's call them context problems. How's that? Okay, so let's do this now. A windlass is used to tow a boat to a dock. Okay, so that's the windlass right there. And I've already created the picture, and I've already put in what my constant value is, which is 15. Now I can get that out of my problem here because it says it's 15 feet below. So when I draw this right triangle, I know that that 15 is going to stay constant. What's not staying constant? Well, the rope is being pulled in, and the boat's also being tugged in. So the x is going to change, and the dx dt is going to go this way, right? And so if the dx dt is going this way and in, then that's going to be negative, right? Because x is shrinking. So if x is shrinking, then we're going to have a negative rate. The rope also is being pulled in, right? At what rate is the boat approaching the dock when there's 25 feet of rope out? Okay, so we're pulling the rope in. So dz dt is also going to be negative, right? These are both going to be negatives because they're being pulled in, and the z is getting shorter. So if your distance is getting shorter, then your rate of change is going to be negative. So let's go and put this together. What form puts together the sides of a right triangle? Hold on, let's label things. Let's label things. If the windlass pulls the rope at a rate of 30 feet per minute, so that's dz dt, right? dz dt is negative 30 feet per minute. At what rate is the boat approaching the dock? So this is what we're looking for, dx dt. When there's 25 feet of rope out, so when z is equal to 25, and we'll use that after we take the derivative. So what puts together the sides of a right triangle? That's it, Mr. Pythagorean, the Pythagorean theorem. All right, so we put the Pythagorean theorem in there, and then we take the derivative. 2x dx dt, every time we take a derivative, we need to make sure we put that in there. The derivative of 15 is just 0. And we have 2z dz dt. Say that 15 times really fast. dz dt, dz dt. Okay, it's going to make you dizzy is what it's going to do. So we got, now we know that the the dock is 20, or the rope is 25 feet out. So we're going to put 25 in for Z. We know that dz dt is negative 30. We don't know what x is, and we don't know what dx dt is because that's what we're looking for. So now how do we find x? Well, x we're going to find by using this idea, using 25 and using my original formula here to solve for x. Remember, I didn't solve for x until after I did my derivative. X squared plus 15 squared equals 25 squared. X squared equals 400. So x is equal to 200. Not plus or minus, right? Because I don't need a negative. This is distance and stuff. So I'm going to take this guy, plug it in right here. And now I'm going to solve for dx dt. I'm going to divide 2 times 200, which is 400, right? And then I'm going to get negative 37.5 feet per minute. I don't want to forget my units. All right, that's dx dt. So there we go. That's a related rate problem. All right, it has the same formula for every one. Okay, so let's take a look at another one, and then you'll see that. Okay, gravel's falling on a conical pile at a rate of 10 feet cubed per minute. So feet cubed, you see feet cubed, you should think, that's volume. So dv dt is 10 feet cubed per minute. The gravel is falling on the conical pile, so that means that if we think about this, this thing is getting bigger, right? So the volume is actually increasing, so that's going to be positive. Find a rate of change of the height. So what we need is we need the volume of a cone. So the volume of a cone is 1/3 pi r squared h. Find the rate of change of the height of the pile, when the radius is 6 feet. At all times, the radius of the cone is twice the height of the cone. So that gives me a different formula, and I think I'm going to put this in red so we can see what we're doing here. That the radius is twice the height of the cone. So I think that's a substitution that we're going to need to make. Anytime it gives us an additional one, we know dv dt, this is what we're going to take a derivative. It's likely we're doing that because we're going to make this substitution in here. So now let's take a moment here. Find the rate of change of the height. So we're looking for dh dt. That's what we're interested in. So do we want our volume in terms of r, or do we want it in terms of h? We want it in terms of h. So that way I felt like Dora the Explorer there. A little pause there for you to answer back to me. So that we can, when we take the derivative, we get dh dt. So we're going to go and make that substitution right now, in that h right here is equal to r over 2. Actually, I want r is equal to 2h because I'm going to plug that back right here for r. So really I'm going to have volume equals 1/3 pi 2h squared times h, which is going to give me 4/3 pi h cubed. Now I can do my derivative. Let's go, guys. Do a derivative. dv dt equals, I'm going to bring that 3 down. It's going to give me 4 pi h squared times dh dt. All right, so let's see. What do I know? I know that dv dt is 10. For pi, I don't know what h is, and I'm looking for dh dt. What do I do? What do I know? I know that the when is when the radius is 6. So how do I find height? Well, I know the radius is 6, and height is going to be 3 by using this right here. So I'm going to plug that right there. 3 squared. Pretty nifty, huh, guys? Hopefully you see that there's a pattern involved, right? So now we're going to divide everything over, and we're going to get dH dt is equal to 10 over 4 pi times 9, which is 10 over 36 pi, which reduces to 5 over 18 pi. What? This is dH dt, so I'm guessing that's feet per minute. All right. There you go, guys. Those are related rates. Follow the steps, and you'll always get them. See you next time. Bye.